collision problem. They give you a bullet with a mass. So this mass is 11.5 grain. The speed of this bullet is 257 meter per second. This is very similar to the lab that you did, the ballistic pendulum, but there's no pendulum. The setup is a little bit different, but it's very similar. Then you should know how to solve this kind of problem. They give you the spring constant, which means how hard, how soft the spring is. The K here is 205 Newton per meter. So Newton per meter is the unit of the spring constant. What is the spring constant used for? Well, the spring constant tells you what is the force of the spring proportional to the change of the length. If you change the amount of the length of the spring, and the spring constant times the change will be equal to your spring force. And they tell you the block and the bullet continue to move and compress the spring by this much before the whole system come to stop. And we're going to assume the surface of the block is resting in resting is frictionless. So there's no friction at all. You don't need to consider about friction. We wanted to determine the mass of the wood. So we going to ignore the mass of the spring. We're going to ignore any of the friction, and we try to find this one here. Okay, and it also tell you when the block and the bullet, they stick together, at this point it's going to be fully stopped. And what is the distance this actually traveled? From here to here is 35.0 centimeter. Okay, so this is your initial. This is your final. And what is the speed of these two things? It's going to stop. Okay, so what kind of collision is this? If they move together, they didn't separate, this is going to be perfectly inelastic collision, just like the previous one. So this is a perfectly inelastic collision. Now, if this is an inelastic collision, the only thing that you can do for the conservation is the conservation of momentum. The energy is not going to be conserved. So you cannot use the conservation of kinetic energy because they move together. So now, how do we find this? If you think about this, would this one completely just the conservation of the momentum? Are there any of external force acting on the object at all? So let's look at the conservation of momentum first and see if we can find a conservation of momentum in this case and look at what happened. So initially, only the bullet is moving and the block is not moving. So your piece of I and there's only one direction, so we don't need like x and y components, so I just simply use the piece of I to represent the x direction. The initial momentum is going to be the mass of the bullet times the speed of the bullet, and plus the mass of the wood times the speed of the wood, and this initially is equal to 0. So our momentum initially is only just the bullet times the velocity of the bullet. So and this is in grain, we have to change it to the kilogram. We're going to divide by 1,000 to get a kilogram, and multiply with the speed, which is 257 meter per second, and kg meter per second is the unit for our momentum. So that's what happened initially. Just right after the collision, meaning just right after the bullet hits to the wood block, I can find what is the speed just right after the collision. So let's find what is the, this, I probably don't want to use the F here because we already use the F here. Let's say V sub C, meaning they're just right after collision. So I want to find what is the velocity at that moment, at the just right after the bullet hits into the wood block. And how do I do that? Well, then you look at what is the final momentum right after the collision. If this is a right after the collision, that means because they are embedded, so the mass should be the total mass of both things. And they are moving with a speed, and that speed is the speed we try to find. So you got the initial one and you got the final one. During the collision, you can use the conservation of momentum, and because it's a perfectly inelastic collision, but it doesn't matter for the momentum, so you can simply just use the momentum. So that's before the collision, or just right after the collision, or I should say just right at the collision. Then you can use this equation to find the speed after the collision. What happened after the collision? After the collision, you are going to have a change of energy, because at that moment you only have the wood block is moving with a speed which give you kinetic energy, and also the spring is also going to store some of the energy, which is what we call the potential energy. So after the collision, because they move with the same speed, but then they have an energy change. So you need to look at the state 1 and state 2. Let me just write the state 1 and state 2 here. And we have a kinetic energy, we have spring potential energy. What do I mean by state one, and what do I mean by state two? Well, state one is this. This is the red wood block, and this is the bullet. So bullet hits to the block and embedded into the block. And this is the spring initially. And the second state is this, is the spring to be compressed. And the bullet and the block moves to a certain distance. At this moment, the V is equal to, let me use state 2, is equal to 0. This one here, the speed is V sub F, which is the one that you, or V sub C, sorry. This is V sub C that you from the previous one. The distance between these two is 35.0 centimeter. Okay, so what is the kinetic energy of the state 1? What is the kinetic energy of state 2? State 2 is equal to 0 because you know the speed is equal to 0. And this one will be 1/2 mb plus nw vc squared. That's kinetic energy. What about the spring energy? At the beginning, the spring is at a rest, so there's no compression at all to the spring. So initially, there's 0 potential energy for the spring. What about the final? Well, final, they told you the distance is 35.0, and that's in centimeter. Then you convert into the meter, and then you use the kinetic potential energy for the spring, which is 1/2 k x squared. X is 35 divided by 100, and this will be in meter square. Then you make these two equal, then you'll be able to find out the solution. Because you know the n sub b, you know, well, you know k, which is given, the 205. What about the v sub c? Well, you find the v sub c from the previous step. So this is very similar to your ballistic pendulum. You have to look at the situation, which part that you can use conservation of energy, which part you can use the conservation of the momentum. So after the collision, we have a conservation of energy.